In 2014, a machine was asked to perform a task it had never done before. It didn't identify a pattern or sort a file. It generated an original human face. It was distorted and eerily flawed, but it was a distinct act of creation. For decades, artificial intelligence was limited to discriminative modeling. Network, the generator, attempts to construct a realistic image. A second network, the discriminator, scans the result. If it spots a forgery, it rejects it with an error signal. This feedback forces the generator to rapidly adjust its parameters and try again. Through millions of iterations, the blurry shapes sharpen into believable approximations of reality as the two networks drive each other toward higher fidelity. The success of this adversarial setup indicated that machines could move beyond static classification and begin to approximate the mechanics of creation. It was the foundational proof that a neural network could learn to hallucinate reality. This timeline tracks to Field's proliferation. In 2014, two isolated nodes, the VAE and GAN, proved digital synthesis was possible. By 2018, transformers and specialized GANs created a dense cluster of progress, moving to complex, high-resolution imagery. Models like StyleGAN achieved a qualitative breakthrough, producing photorealistic human faces. Following the timeline into the 2020s, the methodology shifted toward diffusion and latent models, represented by the rapid succession of nodes leading to DALL-E 2. The velocity of these developments suggests that the primary bottleneck was never computing power. It was the time required to discover the mathematical framework capable of modeling the structure of our world. In the 2020s, researchers refined that framework by inverting the process. Instead of trying to build an image from a blank canvas, they began training networks to find images hidden inside chaos. This is forward diffusion. A clean image, like this drawing of a space elevator, is methodically degraded by adding layers of Gaussian noise at each step until the original structure is completely lost to static. To generate a new image, a neural network called a UNet is given pure random noise. Its task is to predict the noise that was added and subtracted, extracting a brand new image from the static. This calculation takes place in the latent space, a mathematical realm where concepts are stored as coordinates. By operating here, the machine synthesizes high-resolution detail without the computational weight of full image processing. The result is a machine that synthesizes novel concepts from a text prompt. It isn't rearranging existing pixels. It is using its understanding of latent space to render a scene that follows the internal logic of its training data. Mastering diffusion in the latent space gave AI the power to dictate the physics of its own reality, rendering complex, believable worlds from nothing. This capability has immediate, difficult consequences. The field is currently wrestling with ethical crises, ranging from the unconsented use of artist data to the proliferation of indistinguishable deepfakes. However, beneath these practical concerns lies a deeper philosophical question. The methodology of these networks suggests that the act of generation is more than just a creative tool. It is a method of understanding. Physicist Richard Feynman provided a lens for this pursuit on his final blackboard at Caltech. He wrote, "What I cannot create, I do not understand." In AI, recreating the world proves we've modeled its core mechanics. Human intelligence has always followed this axiom. Writers like Charles Dickens didn't just record facts. They generated narratives to map the social and psychological structures of their era, using creation as a way to grasp reality. We have now built a digital architecture that replicates this approach. By forcing a machine to reconstruct our language, our art, and our physics, we are testing its ability to build a comprehensive internal model of our existence. These high-parameter models explore the theory that intelligence itself is a generative process. By training a machine to denoise its environment, we are essentially reverse engineering the way a biological mind predicts and renders its own lived world. In this sense, generative AI serves as a mirror. It reflects the architecture of our own cognition back at us, showing that the path to machine intelligence is paved with the mechanics of the imagination. Surviving the shift toward a generated future requires understanding how the machine thinks, rather than just observing its outputs.